This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on an introduction to sequences and series. Just a quick review on improper integrals. The integral from 0 to infinity of e to the negative 5x dx, we're going to rewrite that using a limit and say the limit as b goes to infinity of the integral from 0 to b of e to the negative 5x dx. Now, to do this integral, it helps to remember that the integral of e to the kx is just e to the kx over k plus c. So the integral of e to the negative 5x would be e to the negative 5x over negative 5. I don't need to worry about plus c, of course, because this is a definite integral. So we get e to the negative 5x over negative 5 as x goes from 0 to b with the limit as b goes to infinity. We can pull this negative 5 out front, so it's negative 1/5 times the limit as b goes to infinity of 1 over e to the 5x as x goes from 0 to b. Plugging in b, 1 over e to the 5b minus 1 over e to the 5 times 0. Now, of course, 5 times 0 is 0, e to the 0 is 1. This part is just 1. But as b gets large, 5b gets large, e to the 5b gets large, and 1 over that would go to 0. So this piece would go to 0, that piece would go to 1. So our result is, of course, 1/5. We're going to look at a sequence now. We're going to say that a sub n is 3 plus n minus 1 over n. So if n is 1, we get a sub 1 is 3 plus 1 minus 1 over 1, or 3 plus 0 over 1. A sub 1 is 3. If n is 2, 3 plus 2 minus 1 over 2, 3 plus a half, or 7/2. If n is 3, 3 plus 3 minus 1 over 3, 3 plus 2/3, 11/3. If n is 4, 3 plus 4 minus 1 over 4, 3 plus 3/4, or 15/4. So we've written down the first 4 terms of this sequence. Now, the limit as n goes to infinity of that will be what? The limit as n goes to infinity of 3 plus the limit as n goes to infinity of n minus 1 over n. And I hope that's obvious, that as n gets large, n minus 1 over n is going to get closer and closer to 1. A million minus 1 over a million, very close to 1. But if you want to formalize it, you would divide top and bottom by n over n minus 1 over n divided by 1 over n. N over n is 1, minus 1 over n over 1, and of course, formally, as n goes to infinity, 1 over n would go to 0. So we get 3 plus 1 minus 0 over 1, 3 plus 1 over 1, or 4. So as n goes to infinity, a sub n, this sequence gets closer and closer to 4. Our next case, we're going to say b sub n is 1, 4, 7, and 10. Is there a way for us to describe this? It looks like the next element is always 3 more than the previous. 4 is 3 more than 1, 7 is 3 more than 4, 10 is 3 more than 7. So we could indeed say the next element, b sub n plus 1, is 3 plus b sub n. Next is 3 more than the previous, and the first element is 1. That would be a way for us to describe this. The other way we could describe this is to say that b sub n is 3 times n minus 2. Notice 3 times 1 minus 2 is 1. 3 times 2 is 6, minus 2 is 4. 3 times 3 is 9, minus 2 is 7. 3 times 4 is 12. Minus 2 is 4. And the fact that these go up by 3 each time told me I should look at 3n. That's the common difference. And then we just had to go ahead and subtract 2 to get it to work in the right direction for us. Here's another recursively defined sequence. We're saying a sub n plus 1 is 3 times a sub n minus 4n plus 2. And a sub 1, our first term, is 5. So if n is 1, replace n with 1. A sub 1 plus 1 is 3 times a sub 1 minus 4 times 1 plus 2. But a sub 1 is 5. So 3 times 5 minus 4 times 1 plus 2. 15 minus 4, 11 plus 2, 13 is my a sub 2. And we can go as far with this as we want. Let's just do a few more terms here. If n is 2, replace that n with 2. A sub 2 plus 1, that would be, of course, a sub 3, is 3a sub 2 minus 4 times 2 plus 2. So a sub 2 plus 1, a sub 3, 3 times 13 minus 4 times 2 plus 2. 39 minus 8 plus 2, we get a sub 3 is 33. And doing one more, n is 3, a sub 3 plus 1 is 3 times a sub 3 minus 4 times 3 plus 2. A sub 4 is 3 times 33, previous term, minus 4 times 3 minus 12 plus 2, 89. And here is another sequence for us to look at. A sub n is 1 minus 2 over n to the n, and I'm interested in terms of what happens to the sequence as n goes to infinity. What is the limit as n goes to infinity of a sub n? Now I'm going to need to use logs, I'm going to need to use L'Hopital, so we're going to make a few minor changes as we go along. First thing, I'm going to call this limit L. Let's take the limit as n goes to infinity of a sub n, call it L, which of course is the limit as n goes to infinity of 1 minus 2 over n to the n. But since I want to take derivatives, I'm going to use x's instead of n's. N implies integers, and I'm a little uncomfortable taking derivatives of integer functions. X implies real numbers, and I have no concern with that. So this limit will be the same as the limit as x goes to infinity of 1 minus 2 over x to the x. To solve this, we're going to take the natural log of both sides. Now the natural log of the limit is the limit of the natural log. And then we can pull the x down in front to say natural log of L is limit as x goes to infinity of x times natural log of 1 minus 2 over x. Pulling that x down front. Now you notice as x gets large, 2 over a large number goes to 0, 1 minus 0 goes to 1, log 1 goes to 0. So this piece goes to 0. This piece goes to infinity. Infinity times 0 is not fair to use L'Hopital. 0 over 0 would be fair, infinity over infinity would be fair. So I'm going to rewrite multiplying x as dividing by 1 over x. Multiplying by x the same as dividing by 1 over x. The top goes to natural log 1 goes to 0. The bottom goes to 1 over a large number, also goes to 0. If we have a 0 over 0 case, we know that L'Hopital is okay. So if we're going to do L'Hopital, take the derivative of the top, take the derivative of the bottom. And this will take a little bit of effort. The derivative of the log of something, 1 over the something, so 1 over 1 minus 2 over x, times the derivative of this, derivative of 1 is 0, negative 2x to the negative 1, 2x to the negative 2 becomes 2 over x squared. The derivative of 1 over x, that's x to the negative 1, negative 1x to the negative 2, or negative 1 over x squared. Now you'll notice that these x squareds will divide out nicely, dividing by negative 1 over x squared, same as multiplying by x squared over negative 1. And we'll get some nice arithmetic there to make our life a little easier. So the 2 divided by negative 1 is negative 2. That comes out front. And I think we have a small error here. Let's fix that. No, take that back. That's correct. That's 1 over 1 minus 2 over x, 1 over 1 minus 2 over x, with the negative 2 pulled out. As x gets very large, 2 over a large number goes to 0. The bottom goes to 1. Negative 2 times 1 over 1 will, of course, give us a limit of negative 2. So if log L is negative 2, then the base of the natural logarithm of e to the negative 2 equals L. And if you remember back to our original question, what was that? That was the limit as n goes to infinity of a sub n. Limit as n goes to infinity of 1 minus 2 over n to the n equals e to the negative 2. Our next example is the sum as k goes from 0 to infinity of 5 times 0.3 to the k. What are we going to do here? We're going to plug in various values for k and see what we get. If k is 0, 0.3 to the 0, we just get 5. If k is 1, that would be 5 times 0.3 to the first, or 1.5. If k is 2, 5 times 0.3 squared, 5 times 0.09, 0.45. K is 3, again, same process holds, and we get 0.135. This example is called a geometric series because to get to each successive term, you multiply by 0.3, by a common ratio. But it is a series, so we're going to add all these up. 5 plus 1.5 plus 0.45 plus 0.135 plus forever. But let's see if we can make some sense out of this. The sum of the first terms, a sub 0, is just 5. The sum of s sub 1, that's a sub 0 and a sub 1, that's 5 plus 1.5, or 6.5. S sub 2 would be a0 plus a1 plus a2, so 5, plus 1.5 plus 0.45, and we get 6.95 for s sub 2, and we could also do s sub 3, which would be adding all 4 of those pieces together, and we get 7.085. But this question is kind of interesting because we can actually determine what that sum will be. So here's what we're starting with. Again, there's a0. The common ratio, r, is 0.3. So a0 is the first term, whatever the first term of the series is. The common ratio is r, whatever you're multiplying by to get each next term. And you need to remember that the infinite sum for a geometric series is going to be the first term over 1 minus the common ratio, as long as that common ratio is small. That common ratio must be between -1 and 1. If that happens, then that series will converge. Indeed, 0.3 is between -1 and 1. So 5 first term over 1 minus common ratio, 5 over 0.7, or 50 over 7 is our infinite sum for that. Approximately 7.1429. But again, remember, the geometric series converges only when the common ratio is between -1 and +1. Here's an example of what we call a telescoping series, 2 over k squared plus k. We're first going to go ahead and do partial fraction expansion. Try to write it as something over k plus something over k plus 1. A times k plus 1 plus b times k over k times k plus 1. The fractions are equal and the bottoms are the same, therefore the tops have to be the same. So 2, this top, equals a times k plus 1 plus bk. Distributing 2 is ak plus a plus bk. AK plus bk is a plus b times k, plus a, is our a there. 2 could be thought of as 0k plus 2. Well, knowing this, 2 has to be the same thing as a, and 0 has to be the same thing as a plus b. Well, if that's the case, of course, b is -2. And we've done partial fraction expansion so that this becomes 2 over k plus -2 over k plus 1. 2 over k plus -2 over k plus 1, written this way. And now we have to find what our partial sums are. I start with a sub 1. If k is 1, notice k is starting at 1. 2 over 1 minus 2 over 2. A sub 2, 2 over 2 minus 2 over 2 plus 1, 2 over 2 minus 2 over 3. A sub 3, k is 3, 2 over 3 minus 2 over 4. A sub 4, 2 over 4 minus 2 over 5. Now the partial sums s sub 1 will be the same as a1. S sub 1 is adding up the terms up to the first one, only 1 here. S sub 1 will be 2 over 1 minus 2 over 2. But S sub 2 will be a sub 1 plus a sub 2. 2 over 1 minus 2 over 2 plus 2 over 2 minus 2 over 3. Minus 2 over 2 plus 2 over 2 cancels. I just get 2 over 1 minus 2 over 3 for S sub 2. S sub 3, add the first, second, and third together. 2 over 1 minus 2 over 2 plus 2 over 2 minus 2 over 3 plus 2 over 3 minus 2 over 4. I just get 2 over 1 minus 2 over 4. And then S sub 4, add the first 4 together. All that's left is 2 over 1 minus 2 over 5. From this, we need to identify a pattern. Notice the denominators keep growing. 3, 2, 3, 4, 5. The denominator 5 is 1 more than 4. The denominator 4 is 1 more than 3. So if I have s sub n, the denominator would have to be n plus 1. So if we're adding up through the nth term, it'll be 2 over 1 minus 2 over n plus 1. That's the pattern we have to recognize. This series converges if this limit of partial sums exists. So we look at the limit as n goes to infinity of that s sub n, which is the limit as n goes to infinity of 2 over 1 minus 2 over n plus 1. This, of course, gets very, very large. 2 over a large number goes to 0. And we will just get 2 minus 0, which will be 2. And that will conclude this lesson.